Okay, so one thing we can do with limits is deal with something we call continuity. Now we talked about it being a function being continuous, and when we said it, it was just, hey, is there no breaks? Is it one connected curve kind of thing? Well, we got a bit more of a definition. Now, in the definition here, the first two doesn't matter on the order. Depending upon what I'm looking at, sometimes I'll do does the function exist? Does the limit exist? Now you think that's enough, but it isn't quite enough. You have to have this last piece. And this is really the big piece here, that the limit actually is equal to the function value. Okay, so let's take a look on the graph. Three-part definition. To prove something's continuous, you have to get all three parts. 2 out of 3, not good. You can't, okay? So let's take a look at example 1a here. At x equal 3, well, what is the limit as x approaches 3 of the function? Well, x equal 3, we're zooming in, and 1. What is f of 3? So the limit exists, the function value is 1. Okay, so the limit exists, the function exists. We have values for those. Now, that's not enough. Don't say, oh, the any fool can see that theorem. Hey, guess what? It's there. Can't do that. You've got to actually state this last part. Actually, if we would be putting it as a sentence, we would say, since the limit as f of x as x approaches 3 is equal to the function value, f is continuous at x equal 3. Okay? So all three pieces, one piece, two piece, three piece, are true. We have a function's continuous. Now, continuous at a point. So B here, at x equal 2. So at x equal 2, again, what I like to look at is whatever, if I'm looking at, hey, look, the limit as x approaches 2 of f of x, as we zoom in here, so as we zoom in here, the function value doesn't approach one particular number. It approaches two different ones, so therefore the function does not, the limit does not exist. So f is not continuous at x equal 2. You only have to violate one of these in order for you to get a no. One for false, all three for true. Okay, by the way, notice how this function, one limit is here, the right-hand limit is 0, left-hand limit is 2. Because of that, this is called a jump discontinuity. And that is when we jump from one value to the next. How about at x equals -1? Again, what are we looking for? Whatever one we want to do first. For me, I'm looking at the graph. I recognize the open circle, the hole there. So that's telling me that f of -1 is undefined or doesn't exist. And since one of those three, the function value doesn't exist, it's not continuous. So f is not continuous at x equal -1. And we would usually call this a removable. Now, one thing to be careful with discontinuity. Now, you might say, well, why do we need that last one if both exist? Well, let's say at x equal -1 if we had the point here, -1, -1. The function value would then exist up here. The limit would be here, but they're not equal. That would not be a continuous function. It wouldn't be continuous function at that point. Again, so when we talk about continuity at a point, no. So that's what we typically look for. Okay? Same thing. This time we don't have the graph. Is the function continuous? Three-part definition. So whatever you want to do first. So let's say if we find what's the limit as x approaches 3 of f of x. Again, start with direct substitution. So 45 minus 9, 36, 37. What is f of 3? You might say, wait a minute, we just did that. Yep. And go, since f of 3 equals the limit as x approaches 3 of the function, notation, 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 f of x is continuous at x equal 3. So three-part definition. 1, 2, doesn't matter the order, 3. B. So let's say if we try what's g of 5 first. Doesn't matter. 5 squared minus 16 over 5 minus 4. 25 minus 16. So the function value exists. What about the limit? As x approaches 5 of g of x. Now you could, by the way, write x squared minus 16 all over x minus 4 right there. Or we could just go ahead and use direct substitution. We end up with, oh look, 9 again. Is the function value equal to the limit? So we write that last sentence. Since g of 5 equals the limit as x approaches 5 of g of x. Function g of x is continuous at x equal 5. Now, when I said things earlier about depends what I'm looking at. You know, when I'm looking at the graph, I could see if the limit, sometimes the limit or the function value jumps out at you. In equation, it may or may not. But for here, rational equation, the reason I started with the function value first is because do I get 0 in the denominator? It doesn't matter if it's removable or we can find a limit. If that function value doesn't exist, g's not, that function g would not be continuous at that point. So here, so what is g of 4? Again, do we happen to have a continuous function? Well, do we have a value of g of 4? Well, yes, we have 0 over 0. That's an indeterminate form for limits, not a limit. This is a function. Function value, as long as you have that function to 0 for g of stuff, that tells you g of 4 does not exist. Therefore, g of x is not continuous at x equal 4. Now, functions can be continuous everywhere else, like this one is, except for here. Now, to tie in, notice, think about, what would the domain of this function be? This rational function turns out to be continuous everywhere on its domain. 4 is not in domain. Okay? How about B? So at x equal -2. So if I try g of -2, that's going to be the first piece. So that's -6 plus 2. Now, what about the limit as g approaches -2? Uh-oh. Weird things happen at -2. Because notice that's where we change pieces. So, in order for us to find the limit, we have to see, is the left side limit, so as g approaches -2 from the left, is that equal to the limit from the right of -2? We don't know that. We got to plug it in. So this left-hand limit, so left hand less than -2, that would be the first one. Right side limit, where x is greater than -2, we still use direct substitution, so we're still going to plug -2 in. So a -2 squared minus 8. Is the left-hand limit equal to the right-hand limit? So therefore the limit is equal to -4. In other words, that piecewise function at -2, this left and right side, left and right hand one, are connected at -2, -4. So the third piece, and again the sentence is important. So since the limit as g approaches of g of -2, and as x approaches 2, the limit of that of g of x are equal, g of x is continuous at x equal -2. So we'll get to the rest on the next part.